Hello. 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 వినిపిస్తుందా? ఓకే ఓకే. అదే వాట్సాప్ లాగిన్ వచ్చిందా? ఓకే 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 ఫైన్. అదే అదే కరెక్ట్. సో ఇదేంటంటే మనము ఐ కెన్ సీ యూ ఆల్సో. ఓకే, సో ఐల్ షేర్ మై వైట్ బోర్డ్. So today we'll discuss few things about problems. Okay, we'll solve some problems. Vapor compression. Okay, vapor compression refrigeration cycle. Okay, refrigeration cycle. Refrigeration cycle. Okay, 1 minute. Okay, so here is the thing we are going to discuss. Okay, so yesterday we discussed, right, what are the important components of vapor cycle, vapor compression refrigeration. Correct. So those are the type of refrigerants. So which, but mainly what I'm asking is what are the important components like processes. Yeah, exactly. So now today we'll solve some problems uh, to deal with the vapor compression cycle. Okay. So in this case, we need to have two important diagrams ready. Okay. So one is your TS diagram. Okay, which is very very important. Okay, so your TS diagram is always like you have a dry saturated curve like this. Okay, then in the dry saturated curve, we represent uh, the cycle, correct? So the cycle. So in the cycle, so let me put this. What is this diagram? This is the TS diagram. So temperature will be on the y-axis, and your just a minute. Okay, temperature will be on the y-axis, and your entropy will be on the x-axis, correct? So here is the entropy, and so I'll write this is temperature to be clear. So that you have to remember this very very uh, clearly, because in order to solve this vapor compression cycle problems, you have to understand this diagram very well. Yesterday also I explained you. See, what is the processes? What are the processes involved in the vapor compression? Is first you have a point. You have a point one. Point one is somewhere here. That's where we start the compressing of the refrigerant. So the compression is going upwards. Why? Because the entropy will be the temperature will be increasing after compression, right? So here is our point number 1, and here is your point number 2. Okay, so that is point number 2. Okay, so what is that process? That process is exactly. So 1 to 2 is isentropic compression. Now, after isentropic compression, what happens? It will be going to the condenser. It will be going to the condenser. So in the condenser, it is a pressure, uh, constant pressure cooling process, right? So it will be like this. Okay, so process will be 2 to 3. The 2 to 3 is a uh, uh, cooling process, constant pressure, heat rejection. Exactly. So here is this is your condenser, right? So you can mark like that. So this is your compression, right? Uh, okay. So let me put it like this: compression. Okay, just for our understanding. Okay, compression. Okay. So this is the condensation. Here is your condensation. Condenser, right? You have a condenser. Okay, now next is after condensation. What is the next process? Expansion. So uh, yeah, 3 to 4 is something like this. Okay, so it is uh, isenthalpic expansion. Isenthalpic expansion. So it will be like this, something like this. Okay, then that is the point number 4. This is your point number 4. Now again, that is the expansion process. So here I will be writing here expansion, right? That is expansion. Then you have a final process, that is your uh, um, what is the final process? Evaporation, right? So this is the evaporation process. This is the that's what evaporation means, nothing but heat absorption. So it will absorb the heat from the constituents in the evaporator. So so you can see that this is the heat absorption, correct? So it is going to absorb the heat. So so that is the, and you have how many processes here? Totally 4 processes. So now at the same time we have to remember one more diagram, which is a pH diagram, which is called a pressure enthalpy diagram. This is a pressure diagram. This is a pressure line. Vertical line is representing pressure, and your horizontal line is representing uh, your enthalpy, right? X-axis is a enthalpy. So I'm just going to draw this line, enthalpy line. 1 minute. So let us say this is the enthalpy line. I mean x-axis. Huh? So here I am going to put the same processes in the pH diagram. Okay, this is called a pressure enthalpy. What is the symbol for enthalpy? H. H. Okay. So if you remember, if you represent the same processes on the pH diagram, so how it will be? You will have a couple of things, like first process is compression process. first process is compression process. So it will be obviously like a curve. 1 minute. So I'm going to draw some lines here. So this is your one curve. So you can see my screen now. So this is one curve, and this is another curve. So everything happens in between these two curves. Okay. So now our process. What is that? First process is a compression process, right? So 1 to 2 will be like this. This is the process 1 to 2 in the pH diagram. So this is 1 and uh, another is 2. Okay. So this is the compression process 1 to 2. Okay. Then 2 to 3 is your, what is the process? Condensation process. So if you remember, condensation happens at constant pressure. That's why this 2 to 3 line will be horizontal line. Okay. So this is a horizontal line in the pH diagram 2 to 3. Okay. Now I'm going to take this one. What is that? Yeah. So 2 to 3 is condensation. After that, what is the process? 3 to 4 is the expansion process, right? But if you remember, the expansion is a isentropic expansion. That means it will be a vertical line, a vertical straight line on the pH diagram. Why? Because it is a isoenthalpic curve, isoenthalpic process. That means the pressure, the enthalpy will be remaining same at 0.3 as well as 0.4, right? So that's why that is a vertical line on the pH diagram. Okay. So now our process, isenthalpic expansion process, is over on the pH diagram. Now I'm going to come back to the evaporation process. So evaporation is process is 4 to 1, 4 to 1. So that is the evaporation process. That's also happening at the constant pressure process. It is a constant pressure evaporation process. Okay. So if you want, again we can write the same thing here. This is a compression. So the cycle is, you have to remember the cycle very well. Okay. Compression, then your compression tarvata condensation. So this is the condensation. Okay. And then expansion. This is your expansion. Expansion in the isoenthalpic expansion. This is okay. And finally we have evaporation. Evaporator, that's where is your heat absorption takes place. So this is what we represented on the pH diagram also. So now our cycle is ready. Okay. Now let us see one problem, as yesterday I told you. So what is the problem here? I have shared you on the Slack. Okay. Just go. I am sharing the Slack already. Just if you are not able to see, just tell me. The Slack I am sharing. Okay. So yeah. So that is there is a problem you can see. Can you read the problem? Anyway, this is this is different. Mm, so anyway, I will explain you. Vapor compression refrigerator works between the pressure limits of 60 bar and 20 bar, 25 bar. So that means they have given the pressures, the maximum pressure and the minimum pressure. Okay. So if you look at our whiteboard, so where you can see the uh, maximum pressure and minimum pressure. So maximum pressure you have to see in the pH diagram. The maximum pressure is happening at point 2 to 3. The process 2 to 3 will have maximum pressure, right? So that is 65 bar, 60 bar he has given, and minimum pressure is occurring at the processor 4 to 1. Okay. So that is the thing. Next, he has given the working fluid under cooling. Working fluid is just dry at the end of compression. So what it means is the compression process. right? We have a compression process. So the compression, after the compression, what is the state of the uh, what is the state of your vapor? Is telling that after compression, my steam is a dry saturated steam. What type of steam? It is a dry saturated steam. That means my point number 2 will be exactly on the dry saturated curve. Okay, that's why I have put the point 2 on that dark line. You see, in the TS diagram, when the compression happens from 1 to 2, at the end of the compression, that means point number 2 will be on the dry saturated curve. You agree? Yeah. So now again, what is the next statement in the problem is, the statement in the problem, it says that uh, there is no undercooling liquid before expansion valve. So that means before expansion valve there is nothing in between. So after the condensation, that means where expansion will come after the condensation. So after condensation, it is going to the expansion valve. There is no undercooler in between. So that is just for understanding purpose. Yes, given sometimes we'll have to see if there is after condensation, that is after 2 to 3, there may be some other intermediate cooling process. Then it is used as undercooling there, but it's not there. It's just giving one statement, but don't worry. So if there is nothing, means after condensation, the next process is expansion. The next process is expansion. So expansion valve, it is going to the expansion. Then after that, it is uh, simply, let's go back to the problem. So after expansion, it is simply going to the uh, evaporator. Evaporator. So evaporator. So after that, it is, we have to find out what is asking. You find out the COP of the cycle and capacity of the refrigerator. Right. So first, look at the table he has given. So the table he says is, what is the pressure at pressure 60? What is the temperature 295? And what is the liquid enthalpy? The next two columns are respected to the enthalpy. Uh, yeah, that is the enthalpy. Okay, and then entropy. Entropy he has given. Why there are two things here is, liquid enthalpy and vapor enthalpy is giving two separate things, right? So what is liquid enthalpy? Ante 61.9. That means whenever he says liquid, means it has to be HF. See, enthalpy symbol is H, but if it is liquid, means it will be HF. Okay, it will be HF. So similarly, if it is vapor, means it will be HG. Okay, vapor means it will be on the dry saturated. It will be on the dry saturated line. It will be on the dry saturated line. So that's what we have to understand. Huh? So that's important. Actually, I want to. So, so he has given, what are the things he has given is, at a 60 bar. See, 60 bar is at this 3 to 4, correct? So at this point, what is the HF? HF he has given liquid, okay, and what is the HG he has given, okay. How do you understand that? See, look at this 3 to 4 process 2 to 3, where the liquid will be. Liquid will be at the end of the 3. I mean, at point number 3. If you see this, I'm putting the arrow right in the whiteboard. So I will draw an arrow for you. See, if I am putting my liquid will be at point number 3. Okay, see this arrow, because after condensation it will be liquid form, correct? So that 60 bar liquid enthalpy is F3. It is F3, HF3, HF3. Same thing at 60 bar, vapor enthalpy will be at H2. it will be at a H2, that is, this is the vapor enthalpy at point number 2, because at this point it is in vapor form. The refrigerant is in a vapor form. That's why it has to be taken as H2. Okay, so that is fundamental difference between the liquid enthalpy and vapor enthalpy. So whenever they say liquid enthalpy, okay, so liquid I am writing here. So liquid enthalpy means HF. Okay, vapor enthalpy means, what is vapor enthalpy? Okay, yeah, vapor enthalpy is HF. Yeah, correct. So I am just giving you vapor enthalpy will be Hg2. Okay. Actually speaking, whatever is there on the dry line, it will be represented as G. Okay. So it has to be Hg2, but at the same time we can write it as H2 directly. H2, because H2 is nothing but Hg2. Okay. So going back to the problem, so at 60 bar we have H2 as well as HF3, correct? So that means whatever he has given at 60 bar, I am writing here on the text, this one, what is that? At 60 bar, right? So at 60 bar, so what he has given liquid enthalpy is HF3, that is, it is HF3, HF3. Similarly, what he has given at uh, point number 2 is H2. Okay, so that is how you have to understand that problem using the data given. So he has given the data like vapor and liquid. That is the enthalpies he has given. So HF3 is 61.9. Looking back the data, HF3 is 61.9. What is that? H2 is 208.1. So that is how you have to understand like that. Okay, na? So at the same time, he has also given the entropies at 60 bar. What is the entropy? Liquid. That means SF. That is SF. Whenever you say liquid, it is SF. Whenever you say vapor, that is SG. Yes, entropy means yes. So it will be SG or S2. You can say. Hmm? So like that. Similarly, if you see the 25 temperature, 25 bar. So going back to the diagram, where is the minimum pressure? 25 is the lowest pressure he has given, right? So if you see the lowest pressure in the diagram, where it is in the uh, point number 4, 4 to 1. 4 to 1 is the lowest pressure. Therefore, he has given that P1 is equal to P4 is equal to 25 bar. At that point, what is the vapor? What is the liquid enthalpy? What is vapor enthalpy? He has given same thing, right? So going back to this uh, slack, you can see the slack problem. Huh? 1 minute. Huh. Okay. COP. So now we have to calculate the COP of the cycle, right? See, what is the formula for COP of the cycle? Huh. Yeah, yesterday I given, right, the problem. So that is, huh. So what is the this one uh, formula? Huh. So here I will write the thing. See, generally speaking, COP is equal to, okay, H1 minus H1 minus HF1, HF3, HF3, H1 minus HF3 divided by H2 minus H1. That's all you have to remember, only this much. Okay. So, Nico, whiteboard confusion. Okay. So here, so you have to, so in this formula, what you have is everything you have, but HF1 you have already. HF1 tells one. So let me show that what are the data. So the data, what it shows is, okay. So you have to calculate H2. Okay, H1. Okay, H1. What is H1? It is at 25 bar. What is the H1? Right? H1 is equal to HF plus X HFG. There is one formula is there, right? H1 is equal to HF plus X HFG. But we don't know the X at point 1, right? So for that purpose, we have to use one relation, that is entropy at point number 1 is equal to entropy at point number 2. See, look at my problem in the Slack. You are seeing the Slack? So I am writing here entropy at point 1 is equal to entropy at point 2, right? That means if I use this relation SF1 plus XSFG1 is equal to, what is the relation? S2. ఎందుకంటే ఇది ఎంట్రోపీ కాన్స్టెంట్ ఎంట్రోపీ ప్రాసెస్. హియర్ యూ సీ ద PV diagram also I have written the TS diagram I have given there, correct? So the TS diagram lo చూస్తే entropy is 1 to 2 is constant, therefore I am equating the entropies from 1 to 2. So therefore I will get the x1, I will get the value of x1. So because you see already he has given the entropies already, so you simply substitute those entropies at point number 1 and 2. Okay. So from that equation you will get the x1. Okay. So therefore you can calculate the enthalpy, that is H1 is equal to HF1 plus X HFG1, right? So if you substitute those all this information, you can get the H1 is equal to, how much you are getting H1? 183.9. You can see the screen, you can see, right? So in this relation HG1, see where he is taking the data, HF1, HF1, HG1, HF1, all this data where he is taking from means he has given in the table. So at point 1, that is at 25 bar problem data. So what is the HF1 means? This is liquid enthalpy is HF1. What is that? Liquid enthalpy is HF1. Vapor enthalpy is a HFG1. Okay. So he is substituting here HFG1. That is, so like that you can calculate the your this thing enthalpy at point number 1. Similarly, what is so H1 tells మనకి H1 we have just now calculated. HF3 already he has given. See what is the HF3? 61.9, because at point number 63 liquid enthalpy is 61.9. that is nothing but HF3, we already noted down. Now H1 tells, H1 we have, HF3 we have, H2 is 208. Why? Because the vapor enthalpy at 60 bar, that is the H2. Okay. So if you substitute all these things, H1, HF3 and H2 in this equation, COP equation, so you can get the COP of 5.04. So this is the way we have to calculate the COP. That is, what is COP full form? Yeah. So now we found the COP. So main important thing you have to remember here is, in order to find the COP, we have to get the H1 enthalpy values at three different points. One is H1, H2, another is HF3. Okay. So in order to get the this enthalpies, we require the dryness fraction X. Okay. So dryness fraction, how you will get is by equating the entropies between point number 1 and 2. So that is how you have to process this problem. So then you found the, what is that, COP already we got. Now the next part of the question is, what is the capacity of refrigerator heat extracted per kg of the refrigerant? So basically capacity of the refrigerator means, see, there is a evaporator, right? So that evaporator, how many tons of refrigeration effect it is creating? Okay, how many tons? See, in our house we have this refrigerator, right? You have this refrigerator, which will be some tons, air conditioner some tons, ice plant, there will be some tons of ice capacity. Capacity is always measured in tons, tons of refrigeration. What is that? Tons of refrigeration. So that is what he is asking to calculate. For that purpose, what we have to do is, first we have to find out what is the amount of heat extracted by the refrigerant. Okay. So how do you know what is the heat extracted? That is nothing but the difference of enthalpy before compression, that is H1 minus H3, HF3, H1 minus HF3. That is always you remember this one. H1 minus HF3 is the heat extracted. Okay. Because even in the COP also, COP formula also, what is COP? Net refrigerating effect by net work done, right? So the upper part, the numerator is nothing but refrigerating effect. The lower part, the denominator is a work done. Okay. So here we are going to use the same formula here. What is the heat extracted? If you know H1 minus HF3, that heat extracted is nothing but you can convert it into tons of refrigeration capacity. Hmm? So how will you do it? It is heat extracted per kg of refrigerant. We are getting 122 kilojoules per kg. You can see the this problem, right? So you are extracting about 122 kgs of heat per kg of refrigerant. Means I am passing 1 kg of ammonia, means it is extracting 122 kilojoules of heat from the system. Understand? So now he has given another information. What is the rate of flow of the ammonia? The rate of flow of ammonia is 5 kgs per minute. Okay, that means for every kg I am extracting 122 kilojoules of heat. If I am sending 5 kgs of ammonia for every minute, then how much heat it will extract? That's nothing but the multiply 122 into with 5. Okay, so for every minute I am extracting 610 kilojoules per minute. Okay, I am extracting a heat of 610 kilojoules per minute from the system. So my refrigerator is doing so much of heat extraction per minute. Now, how to convert this into tons of refrigeration? Okay, that is the what we need to do at the end. See, 1 ton of refrigerant is equal to 3.5 kilojoules per second. Okay, there is a formula. I'll write it for you. Uh, so here I'm giving you, just remember this calculation on the whiteboard. Okay, so 1 ton of refrigeration, 1 ton of refrigeration means, okay, 3.5 kilojoules per second. Okay, so if I am extracting a heat of about 3.5 kilojoules per second, then that means I have done a refrigeration of 1 ton. Okay, is it clear? So remember this. At the same time, if I convert this into per minute, That means 3.5 into 60, right? So that is 210 kilojoules per minute. If I am extracting 210 kilojoules per minute of heat, then it is called a 1 ton of refrigerator. 1 ton of refrigerator. So I can say that 1 TR. See, generally 1 TR means 1 ton of refrigerator. 1 ton of refrigeration. 1 ton of refrigeration means 210 kilojoules per minute. Understand? So using this relation, we can go back to the problem and understand how to convert the how much tons of refrigeration it is creating our uh, evaporator. So see, here we have calculated the heat extracted. Heat extracted is 610 kilojoules per minute. So if I divide this with 210, I will get the number of tons here. So this is the problem. You can find how to calculate the capacity of refrigerator. Okay. So in this problem, we calculated two things. One is COP of the cycle, another is capacity of the refrigerator. So both the things important in solving this when solving this Vapour compression refrigeration cycle problems. So most probably only this type of problem they will ask. Okay. Uh, Anyhow, I will send another problem of the Vapour compression cycle. Just a minute. It is also will be similar. It will be, but the only difference is at the end of compression process. See, in the previous problem, at the end of compression, what is the condition of the steam? He has given the condition of steam is dry saturated. That means the point number 2 will be on the exactly on the dry saturated line, correct? But sometimes the condition of steam after compression will be superheated condition. Understand? So that means the at point number 2, the condition of steam will be superheated steam after expansion, after compression. So in that may be another variation. That is another type of problem. Uh, they may ask. Okay, after compression, the condition of steam is superheated, and they will tell. So that type of problem I am going to show it to you now. So, uh, so just to see the Slack, I have sent one problem. Uh, 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 exact. Uh, so, so here that's what when it is acquiring a temperature of 60 degrees, he is saying, right? That means you can see that the temperature limits. So I will show it on my whiteboard now. So my where is my whiteboard? Okay. So okay. Okay. So I am going to draw a line now. Okay. How the compression is happening from point number 1 to 2 according to this problem. Okay. So my My point number one is always here. What is the point number one? See in the problem how is given. Uh, Point number one is, see, how do you know at the entry to the compressor? Uh-huh. Different, yes, yes, because yes, yes, correct. Why? Because see the condition of steam at the entry of compressor in this problem he has given it is a dry saturated condition. Okay, that means in our in this problem. So I'm going to erase this whole thing 1 minute so that it will be clear because it should not confuse you. Okay, so let me just so see condition of the steam before compression is dry saturated is given. See now as if you see this diagram at point number one, where is the point number one falling? The point number one is falling below the dry saturated line, right? That means it is in the liquid zone. I mean liquid plus vapor zone middle lo undi. చూసావా ఇది left side of the curve is a liquid curve, right side of the curve is a vapor curve, correct? So but in between that, this point is in between that, that means it is a wet vapor, it is a wet vapor. But in this problem he has given that the condition of steam is dry saturated before entering the compressor, right? That means my point one will be on the dry saturated line itself. అర్థమైందా? So because condition of steam is dry saturated అన్నాడు కదా, కాబట్టి బిఫోర్ కంప్రెషన్ అది డ్రై సాచురేటెడ్ లో ఉంది. ఓకే, then he is saying that it is compressed to a temperature of 60 degrees. You see the problem. He has said that after compression the temperature is 60 degrees. That means it is going something like this. Okay, I am drawing that. You can see the curve. So point number two is more than the temperature of condenser. So here this is the only difference in superheated situation. The point number two will be far beyond the dry saturated line. Okay, now that's why what happens is there when you after compression condensation, right? So that it will be condensed in such a way that it will be following this type of curve. Okay, so here it will be. Okay, so we'll call this this particular point as a 2 dash. We will not call this as 2. Okay, previously we said 2, right, in the previous problem, but in this problem when it is superheated we will call this as a 2 dash. Okay, so the condensation happens from 2 to 2 dash, and then from 2 dash to 3 it will be in this fashion if it is a superheated condition of steam. Okay, so this is very important, you have to know before when you solve this superheated type of problems. Okay, so now so the remaining processes will be all same. Whatever 3 to 4 is expansion, that will be same, and 4 to 1 is evaporation, that will be same. Okay, the only difference, two differences in this problem is before compression it is on the dry saturated curve, after compression it is in the superheated state. Okay, now he has given certain things, other things. See at this point what is the temperature at point 2 is 45 degrees. See higher temperature is 45 degrees he has given. Okay, so I'll tell you. So here this temperature is 45 degrees. Can you follow the diagram I'm drawing? This is 45 degrees. But this guy, what is this? This two, point number 2, this is 60 degrees. Okay, because he already gave that the condition of the temperature of steam after compression is 60 degrees, right? So I will be putting this as 60 degrees. So this is the main difference. Okay. So now we have a fair idea about the problem, right? So this is 45, this is 60, and what is the 10 degrees he has given? The 10 degrees is nothing but minus 10 is where will be the minimum temperature in the Vapour compression cycle? It will be in the evaporator chamber, right? Always that will be the minimum temperature. My T1 is minus 10 degrees. Minus 10 degrees. So that is T1 is equal to T4. See, both is same, right? T1 equal to T4 because it is a constant temperature. Okay. Similarly, okay. So these are the information we have. Okay. Now he has given a table also. I sent you one more thing in the Slack. Just look at the next diagram, next sheet. Next sheet is the actual solving of the problem. Okay. So now if you see this problem, how to solve this problem, I have already drawn the same diagram on that whiteboard, correct? So you see same diagram, correct? So 1 to 2, then compression, then 2 to 2 dash, 2 dash to 3, like that. Understand? You are there, Vishnu? Hello? Vishnu. Okay. Somebody disturbed. Okay. So no, never mind. So this is the data he has given. See, at minus 10 degrees, what is my liquid enthalpy? Is 45.4. You can see the screen. So what are the enthalpies given at minus 10? Can you read? No. See that next sheet I have sent. Next. Huh. Enthalpies. Yeah. So that is the HF3. Enthalpy means that is HF3. Sorry, HF1. See, HF1 because 10 is 45.4. So similarly, HG1 is for 460.7. Okay. So here I have written down all the things. HF1 is 45.4. Okay. From the HF3 is 140, 133. H1 is 460.7. Okay, what is H1? H1 means here at minus 10 degrees. What is the vapor? And what is yeah, and what is H2 dash is 483. So H2 is at 0.45. And HF3 is 133. Okay. Okay, why I have written like HF3 and H2 dash for these two things? How I have arrived that 133 is HF3 and 483 is H2 dash. I am writing here, right? How I have arrived is you have to understand that. Okay. See, if you look at this TS diagram, my uh, my liquid enthalpy at 45 degrees. See, 45 degrees line I am showing arrow, right? On the 45 degrees line, liquid, where it is liquid, it is at point number 3, right? So it is touching the liquid curve, right? 3. That why it is HF3. It is HF3. Also vapor enthalpy is on the dry saturated curve, that is H2 dash. H2 dash is some 480 point something, correct? Now what we require is H2. Actually in the COP problem, if you see the H2 COP formula here, I've already written here, right? See this. What is COP formula? H1 minus HF3. Correct. So already we know that H1 తెలుసు, HF3 తెలుసు, right? But H2 తెలియదు. What is H2? H2 తెలియదు. But we know H2 dash. We know H2 dash. So H2 we have to calculate. What is H2 means? H2 means the enthalpy of superheated vapor. Enthalpy of superheated vapor. So there is a formula to calculate what is the enthalpy of a superheated vapor. That is, I will tell you. So here there is a formula. Enthalpy of a superheated is, here you see, H2 is equal to H2 dash plus Cp into, correct. So this I have explained you in the previous units, third unit, like that. What is the superheated enthalpy means? This is a formula. So in order to calculate this, we already know everything. H2 dash తెలుసు, T2 తెలుసు, T2 60 degrees, T2 dash 45 degrees తెలుసు, but Cp తెలియదు. What is Cp? Cp means specific heat at constant pressure of that particular vapor. We don't know. In order to calculate that, first thing is you equate the entropies once again. ఇక్కడ entropies equate చేయాలి. ఎలా చేయాలి? S2 and S2 entropy at point number 2. Okay. Okay. So look at the diagram once again. So um, S2 is equal to, anyway, remember this formula. S2 is equal to S2 dash plus 2.3 Cp into log to the power of log of T2 by T2 dash. There is a formula. Okay. You have to remember this. If you want to calculate a entropy of a superheated steam, then what is the equation is, whatever entropy at the dry saturated line, that is S2 dash, okay, plus 2.3 into Cp log T2 by T2 dash. So if you see the whiteboard, I have given the T2 and T2 dash lines, points, right? T2 and T2 dash, correct? So what is the entropy at point number 2 is entropy at T2 dash plus Cp log T2 by T1. So that is a formula. So if you equate the entropies between these 2 points, then you can calculate the Cp. You can calculate the Cp. So that's what I'm doing here. So you can see that. Sorry, 1 minute. Actually, it's a little bit dull. Okay. So S2 is equal to S2 dash plus 2.3 Cp. So if you substitute all the values of S2 and S2 dash and T2 dash, you already know 60 and 45. Then you have to put it in Kelvin, okay? Kelvin. So 60 degrees centigrade is 60 plus 273 is 333. Similarly, 45 is 318 Kelvin. Okay, you have to put in Kelvin only. Remember that. Okay. Now from this equation you will get the Cp. You will get the Cp. So now your job is easy to calculate the enthalpy at point number 2, H2. So by doing this way, you calculated the enthalpy. H2 is equal to 500 kilojoules per kg. Yes. So now we have all the values in order to calculate the COP. Okay. So COP of the refrigerator, you just see on the left side, I have written vertically the formula. Actually, space was not there. So see left side vertically you see. Yeah. So if you substitute all these values, so then you can get the COP as a, how much you are getting? Yes. So that is the COP of the system. Okay. So this is all we have to understand. If you are solving the uh, superheated type of problems, okay, then if sometimes they may ask calculate the capacity of the refrigerator also, same thing, like once you know what is the heat extracted. So here in this case, always remember COP is nothing but heat extracted divided by the work done, right? So here the numerator will give you the heat extracted, that is 460.7 minus 133 will give you the heat extracted in the by the refrigerator. If you calculate this one, then that divided by 210 will give you the tons of refrigeration, right? So they may ask sometime to calculate the capacity of the refrigerator, right? So for that, you just take the numerator part and then you multiply with mass flow rate. That is very important. See, you have to multiply that with the rate of flow of the ammonia. Then you will get the total heat extracted per minute, right? That divided by 210 will give you the your tons of refrigerant. That is the capacity. Okay. So this is the way to solve the superheated uh, steam in case of a vapor compression cycle. Okay. So I have explained you both the scenarios. Like if the steam is dry saturated, and as well as if the steam is a superheated steam, right? So this way you can solve the vapor compression refrigeration cycle problems. Okay, then I think today I have only these things to explain you. Almost the entire fifth unit is over. So I will send you one more problem. You try to solve that in vapor compression cycle. Okay. So then you will be good to handle this unit 5. Okay. Did you try the other problems which I gave you previously? Okay. Okay, fine. I think the syllabus is over. I'll send some materials like some small questions like that. You can read them. Huh? Okay. So I'll meet you some. If anything doubt is there, you can message me. Okay. Okay, Vishnu. Bye bye. Thank you.